Hello and welcome everybody to the course Crystal Engineering Chemistry Beyond the Molecule. You remember in the last two videos we spoke about hydrogen bonds. We have seen that this hydrogen bonds are a really powerful tool in crystal engineering. We have seen, especially if you're talking about moderate hydrogen bond, directionality is very interesting and very useful in crystal engineering. We have seen in crystal engineering not only strong or moderate hydrogen bond are necessary, you can use weak hydrogen bond, why not? We have seen that it's possible by, I don't know, by if you're talking about acetylene group, something like this, you can really use it in crystal engineering. So all in all, hydrogen bond is one of the dominate intermolecular interaction in crystal engineering. But crystal engineering is not restricted only to hydrogen bond. There is another very interesting upcoming intermolecular interaction, especially in the last years. This is called halogen bonding. And in this video and in the next video I will introduce this intermolecular interaction and will show you, so first I will show you some basics and definitions and geometry energy, and we will have a look how we can use halogen bonding in crystal engineering. Okay, well, as I said, there's a really increasing interest in that intermolecular interactions between halogen atoms by itself. Yes, and if I'm talking about halogen bonding and halogen, I always talk about iodine, bromine and chlorine. Okay, also I'm talking about with three halogens. And halogen bonding is not only restricted to the halogen bonding, also we are talking about halogen bonding. We are talking about halogen bonding with X for halogen and electronegative atoms like oxygen, nitrogen or sulfur. But mostly we are talking about oxygen and nitrogen. If we are talking about X epsilon intermolecular interaction. Halogen bonding is not a new topic in science. This is well known since a long time. It is known since 150 years. Yes. And they found it, and when they saw was short non-covalent contacts in crystals, and if they look to these crystals and these contacts, they saw short contacts between halogen atoms 150 years ago. And in the last, I would say 15-20 years, we see really, I would say, a hype in chemistry regarding halogen bonding. For example, there's a contribution chemistry engineering news from 2009, and this was a report notice about American Chemical Society meeting. Non-covalent interactions akin to hydrogen bonding is becoming an important tool for chemists. 2009, you see, it's not long ago, around about 11 years. We see here a copy paste from the abstract, the nature of halogen bonding and its practical application were discussed at last month's ACS meeting, and so on and so on. We see here a picture, two very nice, demonstrating the applications here. Here's the crystal packing, and here application changing the color, for example, electricity. The aim of the symposium was to draw the attention of the global scientific community to the huge and largely unexplored potential of halogen bonding by presenting its basic concepts, and so on and so on. 2009, you see, what's really, what's I meaning, what's what I want to say with a hype. Okay. And this was 2009, and only some years later, 2012, there was the first satellite meeting from the really big IUCR conference. The IUCR conferences each 4 years, every 4 years, and you see a satellite meeting talking about halogen bonding and categorizing definitions, something like this. It was 2012. And the first symposium on halogen bonding 2 years later, 2014. See it here, no? And you can read or whatever you want, contribution, newsletter, where only what's my meaning, so hyping this topic. A big hello to halogen bonding. So this is Nature Chemistry. Yes, very amazing capital here. No? Amazing headline here, and so on. No? Okay, and here some, how shall I say, pictures, figures regarding this symposium. You see here the molecular arrangement. Very often you see interactions of, here, for example, nitrogen and halogen. Yes, and here halogen. Here very nicely you can see applications jumping here, the charge from one molecule to the other, and you can see how you can use it here, for example, in biochemistry applications. Very often you can stabilize biomolecule by halogen bonding, or you can improve the properties of materials by using halogen bonding, and so on and so on. We will have a look on with different types, molecular application, and their usage in applications. This is a very nicely figure from Metrangolo and Resnanti. Both are big guys, halogen bonding. How you can use halogen bonding, small size ion transporters you can use to improve switch light properties, industrial separation by using halogen bonding. Sometimes if you want to purify anything, it's very helpful. Photoresponsive materials, same background, like switching the color of the light, and so on. In a very broad field, halogen bonding usable. Okay, now we have seen, it seems interesting, it seems useful. When everybody's interesting and everybody thinks it can be have a really powerful potential. Okay, let's have a look on halogen bonding. Halogen bonding, well, similar like a hydrogen bond, is a tool for molecular aggregation. A tool for recognition of molecules in solid state or liquid state. Also comparable with hydrogen bond, it has a robust synton. Yes, robust synton. And the definition of halogen bond is a halogen bond occurs when there's evidence, you see, similar like hydrogen bond, of a net attractive interaction between an electrophilic region associated with a halogen atom in a molecular entity and a nucleophilic region in another of the same molecular entity. You see the similarity to hydrogen bonds? Have a look on the last slides from the last videos. You see you can really compare it. And Metrangolo, as I said, Resnanti is another man. I said both of them. I noticed both of them from big nice discharge also. Now have a look on this halogen bond. What's it? Halogen bond, the basic of halogen bond is a polarization of a carbon halogen bond. Polarization. X, the halogen, is polarized positively in the region that is farthest away from the carbon atom. Polarized positively in the region that is farthest away from the carbon atom. If you read first time the sentence, first you think something like this. C is negative, the carbon is negative, and the halogen is positive. You see directly in this figure this is wrong. So this sentence is not directly clear. Have a look. The electronic charge is anisotropically distributed around the halogen atom. This is the explanation. Yes. If you look to the X, in this case this is like isotropic distribution. This is meaning an isotropic distribution, this is positive and this is wrong. We have an anisotropic distribution, something like this. You see it here. No? We have 3 regions around the halogen atom. We have a negative belt, we have a neutral ring, and in the region that is farthest away from the carbon atom, this is here at the back, there is a positive region. This is called sigma hole. Positive electrostatic cap, sigma hole. And this sigma hole, this is responsible for halogen bonding. The definition, interaction with electronegative atoms, nitrogen, oxygen, halogen, where negatively charged region is present. And if you look, comparable to hydrogen bonds, you will see that the difference, the distance of these 2 atoms, similar like hydrogen bond, is shorter than the van der Waals radii. And this is a very interesting notice, very important notice. The depth of the sigma hole directly correlates the intermolecular interaction strength. And this issue is not comparable with hydrogen bonds. In the case of hydrogen bonds, the strength of hydrogen bonds is not really tunable. In the case of halogen bonding, it is tunable. And by tune the depth, you have the possibility to improve the strength of the intermolecular interaction. You see the depth of a sigma hole. This is the ranking: iodine, bromine and chlorine. No fluorine. Yes. Why? Very nicely shown here in this contribution 2008 in Angewandte Chemie. This is a molecular electrostatic potential of of halogenated carbon, tetrahalogenated carbon. Yeah? Well, what you see in the case here, the fluorine, there's no always the same, always the same distribution of the potential. If you look, for example, here in the case of CF3 iodine, what you see is here this very nicely difference in the molecular electrostatic potential. Here, it's possible that this region is useful in halogen bonding, in contrast to here, in this moment. This is the first thing, talking about the depth, the possibility. Now have a look on the geometry. If you're talking about the geometry in halogen bonding, we're talking about this unit here. This is one unit, see carbon halogen on one side and the other halogen carbon on the other side. So there are two possible types of halogen bonding categorized, type 1 and type 2, and they are based on the angle. One is symmetrically conformation, and the other is something like this here, 180 and 90 degree. Here theta 1 and theta 2 are equal. Parallel, electrostatically identical region. There's no difference. In this case, you remember talking about the anisotropically distribution, electronical distribution around the halogen atom. Here is the positively charged, and this is here the belt, the electronegative belt, the negative belt. So we have the interaction of the positively charged region and the negatively charged region. And this is mostly what we predict if we use this theory of sigma hole to explain halogen bonding. Positive polarization, the polar region of a halogen atom, and a negative polarization in its equatorial region, the negative belt. Yes. On the other side, so we have these two types. On the other side, if we now look in the Cambridge Structure Database, it is not so easy to assign all structures clearly to, for example, here this predicted geometry of halogen bonding. Have a look. An analysis, a survey about around about 100 structures of halogen substituted benzenes. So this is a very robust backbone, and we only switch the substitution pattern and the number of a halogen at the aromatic backbone. Yeah. So this is the result. We look to fluorine-fluorine, chlorine-chlorine, bromine-bromine, and iodine-iodine interaction. Green one is fluorine. Here, yes, how shall I say? Slightly green is chlorine, blue one is iodine, and the black one is bromine. You see here the lines, genau here, with lines, with dotted lines. This is the borderline for van der Waals rally. So it means, for example, if we're looking here the fluorine, so we have here this interaction distance from 2.8 to, I don't know, 3.1. Yes, and here on the right side of the borderline, these distances are higher, longer than the van der Waals rally. Okay? Okay. So first what we see is that not all interactions, not all distances of chlorinated or halogenated compounds are below the borderline. Yes, you see, for example, in the case of iodine, most of them are longer than the van der Waals rally. Also in the case here with the chlorine compounds, or in the case of bromine. So, this is the first result. The second thing we talk about the angle. Yeah. Now in this figure we try to analyze the angle. You remember? The angle is the key function to distinguish between type 1 and type 2 halogen bonding. Well, now here you see the angles theta 1 from, 70 degree to 180 degree, and theta 2 from 80 degree to 180 degree. And we try to address all contacts in three regions, or distances, no? A, B and C. In region A, the angle of theta 2 is below 90 degree. Well, this could not address to type 1, type 2, so we said, okay, we ignore this region. In this region, region C, this is exactly what we predict suggests in type 1. Type 1 is similar, equal angles of theta 1 and theta 2. No? 120 here, 120 over the red dot here. No? This is exactly what we would predict here. It's always the same. No? So with 25 contacts or intermolecular interaction could be clearly addressed to type 1. Type 2, this is the type with a positive sigma hole and the negative electronic belt, which is what we predict for typical halogen bond. With intermolecular interactions or the distances, could be addressed to region B. What means only 25% of the investigated 100 structure could be clearly addressed to type 2. That's what I mean. It is not so easy to clear address halogen bonding to type 1 and type 2. You remember, you can a little bit compare it, thinking about remember in the case of hydrogen bond, talking about carboxylic acid? First thing, the first moment we would address the formation of this dimers, the dimer of carboxylic acid. But if you look in the crystal structure database, only 33% of carboxylic acids form this dimer. Comparable situation in the case of halogen bonding. Sometimes reality is not so easy. Okay, here are only 3 interesting contributions regarding halogen bonding, but if you look in the literature and we look in the SkyFinder database, you will find a huge number of contribution regarding this topic, halogen bonding. Okay, see you in the next video.